Reactions of alcohols. The OH functional group conveys a lot of reactivity to the alcohols. We're going to look at two principal reactions, dehydration and oxidation. When dehydration occurs, a molecule of water is removed from the structure of an alcohol. If we were to use some lasso chemistry, it would be like this. And the agent that causes this, or the catalyst, is sulfuric acid. And so it's placed above the arrow. 180 degrees centigrade are conditions that promote this kind of dehydration. And when a water molecule is removed from the structure, it leaves behind the carbon-carbon double bond. And this is because carbon, the magic number is 4 bonds. And so if we remove these two groups, the only way carbon can achieve the 4 bonds is if that double bond forms, and water is the other product. An alcohol, in words, is converted to an alkene. Give an example. When the OH is removed from the structure of an alcohol, it takes with it a hydrogen on a neighboring carbon. That means this hydrogen or this hydrogen up here, and not a hydrogen that's on the same carbon as the OH. So typically there are two possible products. As we remove that water molecule, we could form the double bond there if this were the water molecule that's being removed, or the other possibility would be this one. And in this case, they're both the same. If we were to give this structure a name, it's cyclopentene, and this too is cyclopentene. The fact that the two names are the same is our clue that the structures are identical too. All we'd really have to do is rotate that structure a little bit, and we'd see that they're the same. That isn't always the case. Here in this structure, we've got 2 butanol. And as the OH is removed, it could take with it a hydrogen from this position or the 3rd carbon. And so there are 2 possible products. And I've shown the carbon skeletons here on the right-hand side just to make it a little easier to see the carbon-carbon double bond. If this were the hydrogen that were taken, the double bond would be between positions 2 and 3. If it removed the hydrogen from the N carbon, then we'd have the double bond between 1 and 2. Well, it turns out that this is the favored product. We get a lot more of this than we do this one down here. And so it gave rise to a rule that helps us predict the major product when a dehydration of an alcohol occurs. The product that tends to form is the one in which the carbon-carbon double bond has the most carbons attached. And if we, well, let's expand both of these carbon-carbon double bonds. These carbon-carbon double bonds and count the carbons that are directly attached to those double bonds. To be able to accurately predict which of these 2 products will form, I've expanded the structure a little bit, and I've just shown the carbons primarily. Here's the carbon-carbon double bond, and I see that this carbon and this carbon up here are directly attached. So there's 2 carbons attached to this carbon-carbon double bond. Over here, here's the carbon-carbon double bond. We've got 3 hydrogens. That means that there's only 1 carbon, this one right here, that's directly attached to the carbons of the double bond. So this one is the winner. This is the major product, and this one, sometimes we don't see any of the minor product. Let's look at another example. Here I've got Let's look at another example. Here I've got a cyclohexane ring. We've got an alcohol and another group attached. We're going to treat it with sulfuric acid, 180 degrees centigrade. We know that a water molecule is going to be pulled out. Sulfuric acid, we say, is a dehydrating agent. It has a strong affinity for water, and if you happen to get some sulfuric acid on your skin, in just a couple of minutes it starts to form a blister because it's doing the same thing to your skin. It's pulling that water to the surface. Two possible products. Then, if this hydrogen, we've abbreviated it so that it's not shown, but if this hydrogen and this OH were removed, we'd have the double bond here. If this hydrogen were pulled out along with the OH, we'd have the other product shown on the right-hand side. Which of these is the major product? The reason that I chose this particular example, one edition of the text has an error, and it's a terrible error. I'd like to believe it's a typo and not an error, but it shows this as the major product, and that's not true. It's this one right here. And the reason, if we were to count the carbons that are directly attached to these two carbons here of the double bond, we'd find that there's 1, 2, 3. 3 carbons on that carbon-carbon double bond. Over here, we have just 1, 2 that are attached. So this is the winner. This is the major product that's formed. There's another way that we can remove water from an alcohol. There's another way that we can remove water from an alcohol, and in this method that I'll show you here in a second, it produces an ether rather than an alkene. If we use sulfuric acid as a catalyst and slightly less severe temperatures, 140 degrees centigrade, there's another way that we can remove a water molecule from alcohols. Using some lasso chemistry again, what if we had 2 alcohols positioned so that we could remove this water molecule between the 2 molecules? This is going to bridge these 2 structures. Water is going to be one of the products. The other product will link this carbon and that oxygen. And as it does so, it produces the structure on the right. And this is an ether. It's an oxygen positioned between 2 carbons. That's the ether functional group. Let's look at another example of that reaction. What if I had 2 cyclopentanols and treated it with sulfuric acid, 140 degrees centigrade? Again, we're going to remove a water molecule from between these 2 structures. As we do so, water is one of the products. The other product links these 2 structures together, and so we have the ether functional group bridging the 2 cyclopentane rings. The second reaction of alcohols that we'll look at is the oxidation of alcohols. Here's the structure of an alcohol, and this O in parentheses symbolizes an oxidizing agent. Could be something like potassium dichromate or potassium permanganate. And these are substances that have the ability to remove hydrogens, 2 hydrogens from this structure, one from the OH, one from the carbon that the OH is attached to. As it does so, to balance the equation, we've shown O and the 2 H's forming water. The other product, well, if we remove these 2 atoms, the only way carbon can have 4 bonds if there's a double bond between the carbon and the oxygen. And oxidizing agents and oxidation of alcohols is a pretty common reaction. Here I've got an oxidizing agents and oxidation of alcohols is a pretty common reaction. Here I've got a primary alcohol. You remember that a primary alcohol is one in which the carbon that contains the OH is attached to one other carbon. The oxidizing agent is going to remove 2 hydrogens. As it does so, the position of the oxygen stays on that same carbon. Got a C double bond O. Because there's two hydrogens here, as we take one of those, there's one left. The other product is water. This is a new functional group for us. That C double bond O with the hydrogen attached is called an aldehyde. It's a secondary alcohol. In this case, the OH is attached to a carbon, which is attached to two other carbons. That makes it a secondary alcohol. Upon oxidation, the double bond is going to form at the same position, plus water. When we have a C double bond O that's between two carbons, rather than on the end of the chain, it's called a ketone. Let's look at the oxidation of a tertiary alcohol now. Here's the structure of a tertiary alcohol. The carbon that has the OH is attached to three other carbons, plus an oxidizing agent. Turns out there's no reaction. These alcohols can't be oxidized. Let's see if it makes sense why. Here's the OH. It could be pulled out, but there's no hydrogen on the carbon that the OH is attached to. Got lots of neighboring hydrogen, but that's not the oxidation reaction we've been studying. Hydrogen would have to be attached to this carbon in order to leave with the OH. Just as an example now, here's cyclohexanol. What is it? Primary, secondary, tertiary? Well, the carbon that has the OH attached is attached to these two carbons. That means that it's a secondary alcohol. It's going to produce a ketone. Here's the structure of the ketone, plus water. The O stays at the same position. Down here, well, now this carbon that has the OH doesn't have any hydrogens on it. It's attached to three carbons. It's a tertiary alcohol, can't be oxidized, no reaction.